Way back in 1959, the physicist Richard Feynman gave this incredibly famous lecture called There's Plenty of Room at the Bottom. He posed this wild, borderline science fiction idea about basically swallowing the surgeon.
Right, the ultimate dream of minimally invasive medicine.
Exactly. He envisioned injecting a microscopic autonomous robot into the human body, letting it navigate the bloodstream, and just having it perform precise medical interventions without ever making a surgical incision.
And it remains the ultimate benchmark.
Mm-hmm.
But that vision has stayed stubbornly out of reach for, well, over 6 decades now.
Yeah, because of the propulsion physics, right?
Exactly. The physics of propulsion at that microscopic scale, what we call life at a low Reynolds number, where fluid viscosity completely dominates over inertia, are just incredibly unforgiving.
You're effectively trying to swim through molasses.
That's the perfect way to picture it. You're trying to swim through molasses, and the engineering required to generate persistent directed force in that environment is staggering.
Well, today we are looking at a breakthrough that might finally crack that engineering problem. And for those of you listening who spend your days operating two-photon polymerization systems, staring at your voxel parameters, this is a look directly into the future of your field.
It really is.
Because the solution to Feynman's dream is being built right now using the exact 2PP toolkit you rely on every day.
And we're looking at a pretty rare, fascinating moment of synchronicity in the scientific literature today. 2 highly detailed, just massive papers were recently uploaded to the arXiv preprint server by 2 distinct research groups.
Right, we've got a team led by Jegel and Witkowski out of Germany, and another by Fischer and Betz, also based in Germany.
Yeah, and they clearly coordinated to sync their uploads to avoid scooping one another.
Which, always signals that the findings are substantial, like they knew they had something big.
Absolutely. Both groups are using 2-photon lithography to manufacture SPRAT particles. That stands for symmetry-broken refractive-index profile particles.
So, to put it simply, they're printing fuel-free, light-propelled microrobots.
Exactly. And what they are doing with 2PP here directly targets the most stubborn roadblock in active soft matter, which is the fuel problem.
Right, because up until now, the traditional workhorses of micropropulsion have been chemically powered micromotors, right? The Janus particle.
Yeah, Janus particles. You fabricate a particle with 2 different faces. You might, say, coat one side in a catalyst like platinum, and you drop it into a solution containing hydrogen peroxide.
And it reacts.
Right, the platinum catalyzes a decomposition reaction, and that local chemical gradient physically drives the particle forward.
Which, that mechanism makes sense in a petri dish, but the limitations for biological applications are immediately obvious. Hydrogen peroxide is highly toxic.
Highly toxic. You absolutely cannot flood a patient's bloodstream with hydrogen peroxide just to power your swallowed surgeon.
Yeah, that's a non-starter. And furthermore, the particle is actively consuming its chemical environment, meaning the mission has a hard expiration date based on, well, fuel availability.
Right. And beyond the toxicity and the fuel depletion, the chemical decomposition creates these really complex, chaotic, hydrodynamic flows in the surrounding fluid.
Like a turbulent wake behind a boat?
Exactly like that. And if your goal is to have a coordinated swarm of thousands of these microrobots targeting a specific tumor, those turbulent fluid flows completely interfere with one another.
Oh, I see. The chemical exhaust of one particle disrupts the trajectory of its neighbor.
Yeah, which makes swarm coordination almost impossible.
So that pretty much rules out chemical fuels for anything inside the human body. The alternative is usually external fields, magnetics, acoustics, or light.
But light historically comes with its own severe limitations in this context.
Because conventional optical actuation relies heavily on absorption, right?
Exactly. A laser illuminates the particle absorbs the photon energy, it heats up, and that thermal gradient drives motion through photothermal propulsion.
And localized heating is just disastrous when you are operating near delicate biological tissues. You don't want to boil the blood.
You really don't. But even from a pure physics standpoint, absorption fails when you try to scale up to a swarm.
How so?
Well, imagine a dense, 3-dimensional suspension of these absorbing particles. The particles at the front of the swarm absorb the incoming laser light. But by doing so, they cast this deep shadow over the rest of the suspension.
Oh, wow. So the particles in the back receive virtually zero energy and just remain completely static.
Exactly. So we're boxed in, chemical fuels are toxic, and absorbing light boils the surrounding fluid while blinding the back of the swarm.
Which is where these papers come in. The breakthrough in both the Fisher and Jeggle papers is abandoning absorption entirely and relying purely on refraction.
Yes, momentum transfer through bending light.
Right. So they are printing polymer particles that are highly transparent at the targeted laser wavelengths. The light passes right through the structure, but because the refractive index of the polymer is higher than the surrounding fluid, the light bends.
And conservation of momentum dictates that if you change the directional vector of a photon, the object that caused that change, in this case, the polymer particle, must experience an equal and opposite force.
So when the light exits the transparent particle at a new angle, the particle itself receives a physical push in the opposite direction.
Precisely. And this completely circumvents the thermal heating problem. It provides continuous energy as long as the external light source is active.
And because the particles don't absorb the photons, the light penetrates deeply into dense swarms without that shadowing effect you mentioned earlier.
Exactly.
I picture a perfectly transparent sailboat. Instead of a canvas sail catching the wind and moving via pressure, the sail just slightly redirects the wind as it blows straight through it, giving it a push.
That's a great analogy. But to get any meaningful forward thrust out of that, the redirection of the light has to be highly asymmetrical.
Right, because if I just take a 2pp system and print a perfect sphere, the laser light enters, bends symmetrically, and exits symmetrically.
Yeah, in that case, the lateral force vectors just cancel each other out, and the particle just sits there vibrating from Brownian motion.
So to generate persistent directed velocity from optical momentum, you have to fundamentally break the symmetry of the light path.
You have to physically shape the particle so that photons entering from one direction are consistently bent in an asymmetric pattern. And this is precisely why both teams turned to two-photon polymerization.
Let's examine the fabrication strategy, starting with the Fisher Group. They used a commercial nanoscribe photonic professional GT2 system, right?
Yeah, and they printed with the widely utilized IP-DIP2 resin. To prove the fundamental concept of broken symmetry, they printed two distinct geometries onto a fused silica substrate.
Perfect spheres with a 5-micron radius as their control and a design they call bullets.
And the bullet geometry is just a masterclass in functional simplicity. It consists of a 5-micron hemisphere at the leading edge fused to a 20-micron long solid cylinder at the trailing edge.
Okay. And when they suspended these in water and illuminated them from below with a homogeneous 532 nanometer laser,
the broken symmetry of that flat cylindrical back versus the curved hemispherical front caused massive optical momentum shifts. The bullets exhibited clear ballistic directed motion,
proving that macroscopic shape asymmetry in a transparent 2pp print successfully creates a light-driven motor.
Exactly.
But, the data on their control group is fascinating, especially for anyone listening who spends their days fighting voxel resolution limits.
Oh, this part is brilliant.
Fisher noted that even their supposedly perfect control spheres exhibited a tiny but measurable amount of directional motion. And a perfect sphere mathematically shouldn't do that.
No, it shouldn't.
So does a standard 400 nanometer voxel size inevitably cause micro imperfections that ruin perfectly symmetrical optical traps?
It does. It is a critical reminder of the gap between the digital CAD file and the physical print. A 2pp voxel is not an infinitely small point. It's an ellipsoidal volume of polymerized resin.
Right, they have physical dimensions.
Exactly. When you discretize a smooth spherical surface into a finite number of slicing layers, you inherently generate nanoscale ridges. Sometimes people call them stair-stepping artifacts.
Yeah, we see this all the time under some.
Right. And at the scale of optical wavelengths, those slicing ridges act as unintended diffraction gratings. They scatter the light asymmetrically.
Oh, wow. So combined with slight anisotropic shrinkage during development, you end up with localized scattering points that break the perfect symmetry.
Yeah. The host fluid doesn't see a perfect sphere. It sees a subtly textured, optically asymmetrical object.
So you think you printed a sphere, but optically you printed a very weak, confused bullet.
That's a great way to put it.
That brings us to the Jeggle Group. They built a custom TPP setup using a femtosecond laser operating at 780 nanometers.
Right. And they utilized Ormocomp photoresist, which is a hybrid organic-inorganic polymer known for its incredible optical transparency.
And they systematically attacked the geometric design space. They printed solid hemispheres, solid cones, caps, which they define as hemispheres with a spherical cutout at the base, and cornets, which are hollowed-out cones.
Now, a macroscopic intuition of fluid dynamics might suggest that hollowing out the back of the particle, creating a shape similar to a parachute or a cupped hand, would increase propulsion by sort of catching more light.
Sure, like a parachute catching air.
But optical physics operates under completely different rules. Jegel's group proved, both physically and through rigorous ray tracing simulations, that the hollowed-out shapes like caps and cornets actually produce significantly less forward thrust than their solid counterparts.
Wait, why does removing that material drop the force? I would have assumed the parachute shape would be better.
It all comes down to where the momentum transfer is most concentrated. When light propagates through the solid hemisphere, a massive portion of the net forward force is generated at the planar interface, the flat bottom of the particle.
The flat base.
Yeah. As the photon tries to exit the dense polymer and enter the lower index fluid, a large fraction of that light undergoes Fresnel reflection. It bounces off the flat internal surface and reverses direction.
Oh, I see.
And that complete reversal of the photon's momentum vector delivers a massive physical kick to the particle.
So when you hollow out the base to make a cap, you are physically deleting that flat planar interface.
Exactly. You replace a high reflection balance with a gradual transmission gradient, and you fundamentally lose the most efficient momentum transfer mechanism in the entire structure.
That is a phenomenal insight into optical engineering. The very surface you might think is just dead weight or aerodynamically bulky is actually the primary engine.
It is. But Jegel's team didn't just stop at manipulating external geometries. They tackled internal symmetry in a way that truly pushes the limits of what 2pp can achieve.
Right. They figured out how to keep the outside of the particle perfectly symmetrical while breaking the symmetry internally. They created gradient index, or GRI, profiles.
And the fabrication technique here is demanding. I mean, anyone who operates these lasers knows the nightmare of optimizing laser power.
Oh, absolutely. If you push the intensity too high, you risk microexplosions, literally boiling the monomer resin and destroying the print.
And if it's too low, the structure simply washes away during development.
So they had to ride the line.
They rode the absolute edge of that power threshold. During the printing of a single particle, they dynamically swept the mean laser power from 0.45 milliwatts at one side to 0.77 milliwatts at the other.
Because in 2pp, the intensity of the laser dictates the local cross-linking density of the polymer network. And a denser, more tightly cross-linked polymer has a higher refractive index.
Exactly. They leveraged that property to continuously tune the refractive index of the ormocomp from 1.499 to 1.511 across the z-axis of the particle.
But doesn't that introduce a severe complication? Like when you increase the laser power to increase the cross-linking density, you also inherently inflate the size of the voxel.
Yes. It's a huge complication. If you just sweep the power inside a standard spherical CAD file, one side of your sphere will just bulge outward.
So how did they fix it?
They had to mathematically compensate for that voxel inflation directly in their slicing software to ensure the final outer geometry remained a perfectly smooth sphere or hemisphere.
That is a staggering level of process control. It's a bit like a loaded die in a casino.
A loaded die.
Yeah, from the outside, the die is a perfect cube. It rolls smoothly, and the aerodynamic drag is perfectly symmetrical on all sides. But internally, the density is shifted, forcing it to behave asymmetrically.
That's spot on. By printing an internal GRN profile, the particle remains perfectly smooth on the outside, maintaining consistent, predictable hydrodynamic drag in the fluid.
But internally, it is optically weighted.
Right. The light hits that refractive gradient and bends asymmetrically inside the sphere, generating lateral thrust without relying on complex external shapes.
Which is huge, because the ability to decouple the propulsion mechanism from the hydrodynamic profile is a massive leap forward.
It really is.
Yeah.
In standard microrobotics, modifying the shape to get more speed almost always alters how the particle interacts with the surrounding fluid or, biological tissue.
Right. A sharp edge might give you better optical thrust, but it could cause turbulence or even damage a cell wall.
Exactly. The GRN profile allows you to design the exterior geometry purely for safe, efficient navigation through a delicate environment, while tuning the interior optical gradient purely to maximize light-driven thrust.
So we have two incredible tools now for our listeners' toolkit: Fisher's external geometric manipulation and Jegel's internal density gradients. But if the goal is swallowing the surgeon, speed is critical. A microrobot cannot take 3 days to travel down an artery.
No, it can't.
So how do we maximize the sheer velocity of these refractive momentum engines?
Well, the Fisher group ran exhaustive optical simulations to discover the theoretical limit of refractive thrust. They analyzed Snell's law and the specific critical angles between their IP-dip polymer, which has a refractive index of roughly 1.5 in water, sitting at 1.33.
And what did they find?
They found a definitive winner. It's a specific geometry they termed the right trapezoid.
It looks exactly like a microscopic skateboard ramp.
It does. And the right trapezoid is the holy grail of thrust because it relies entirely on total internal reflection, or TIR.
Ah, TIR.
Yeah. They engineered the specific angle of the trapezoid's back wall so that when the homogeneous light enters the flat bottom of the particle, it strikes that slanted ceiling exactly at or above the critical angle.
So instead of refracting out into the water, 100% of the photon energy is internally reflected sideways.
Sideways. And then it hits another wall to bounce completely backward. There is zero transmission loss out the back of the particle.
Oh, wow. So it's a perfect momentum trap.
It is. And their calculations show it generates more than 5 times the forward thrust of their standard bullet designs.
5 times the speed is incredible, but the Jeggle group is thinking beyond single isolated particles racing down a track, right? They're looking at the macroscopic potential of these S-Brive particles.
Yes, they introduced the concept of volumetric active matter.
Which is fascinating.
They envision a massive, three-dimensional swarm of these transparent particles suspended in a fluid. Because they don't absorb light, a single broad laser beam can illuminate the entire swarm simultaneously.
And when the light hits, the particles begin to move based on their shapes or internal gradients.
Right. And as the particles translate and rotate, the overall refractive index of that specific volume of fluid dynamically changes. You have highly refractive polymer structures migrating into spaces previously occupied by lower index water.
Okay, so as the local index of the swarm fluctuates, it physically alters how the light propagates through the rest of the suspension.
Exactly. The light drives the particles, and the reorganized particles act as a dynamic lens, focusing or scattering the light field in real time. It basically creates a closed feedback loop between the optical energy and the material structure.
Okay, let me push back on the reality of that for an in vivo medical application, though.
Sure.
It sounds beautiful in a static cuvette of pure water on an optical table. But blood is not a static water bath. You have red blood cells, proteins, white blood cells. It is an incredibly noisy, chaotic optical environment.
It is very turbid.
So if you have a swarm of polymer particles dynamically lensing and shifting the refractive index, wouldn't that just cause massive, unpredictable optical scattering? You'd be firing a laser into a pulsing fluid that is actively trying to scramble your beam.
You're absolutely right. That is a highly valid critique of the whole swallowing the surgeon timeline. Right. In a highly scattering environment like whole blood, creating a stable, self-organizing optical feedback loop over deep tissue distances is, well, it's currently beyond our reach.
Yeah.
The immediate applications for volumetric active matter will likely be in isolated microfluidic chips or localized tissue interactions where near-infrared light can penetrate safely, or even in creating adaptive metamaterials that operate completely outside the body. The fundamental physics of the swarm, acting as a computational adaptive material, are sound. But translating that specific behavior into deep tissue chaotic blood flow will require significant advancements in overcoming biological optical scattering.
Which grounds the research, but, I mean, it doesn't diminish the incredible achievement of solving the fuel problem in the first place.
Not at all.
Let's synthesize what these two phenomenal papers have delivered to the 2PP community. We finally have a path away from toxic chemical micromotors and tissue-damaging photothermal heating.
Yes, instead we have direct optical momentum transfer utilizing highly transparent S-Brive particles.
Right. And Fisher's group proved that breaking external shape symmetry creates reliable motion, and they identified the right trapezoid as the ultimate geometry for raw speed via total internal reflection.
And Jegel's group demonstrated the precise execution of dynamic laser power modulation to fabricate internal Jimin profiles. They proved we can decouple the propulsion mechanism from the physical shape,
allowing for smooth, biologically friendly exterior designs that still harness asymmetrical optical forces. It's a massive leap forward.
Huge.
But I want to leave you, our listeners, with an engineering challenge that sits squarely at the intersection of both these papers. An idea to explore on your own systems. What if you combine them?
Ah, the composite approach.
Exactly. Imagine taking your GT2 or your custom femtosecond setup and printing Fisher's high-thrust right trapezoid.
Okay.
You utilize that external geometry to capture 100% of the photon momentum via total internal reflection, guaranteeing maximum ballistic speed. But an object relying entirely on TIR is notoriously difficult to steer laterally.
Right, so just go straight.
So you employ Jekyll's technique. You dynamically modulate your laser power during the printing of that right trapezoid to embed a complex GN profile inside it.
So you embed a localized refractive index gradient within a shape designed for total reflection.
Right. Could you create a microrobot that uses its external geometry for raw, massive forward velocity, but relies on a tunable, asymmetrical internal gradient to act as a microscopic steering wheel?
Oh, that's brilliant.
You illuminate it with one specific wavelength or polarization to drive it straight via the TR interfaces, and then you shift to a secondary wavelength to activate the internal drawing gradient, generating lateral force to steer it through an arterial junction.
So you get the microscopic sports car and the precision steering rack,
hmm
entirely manufactured within a single droplet of photoresist.
Exactly.
I mean, the optical physics absolutely support the concept. The difficulty lies entirely in the execution. You'd have to perfectly align the geometric TR interfaces with the voxel-by-voxel modulation of the internal refractive gradient without inducing catastrophic structural defects.
It's the exact kind of complex, multifunctional voxel-level engineering that makes two-photon polymerization such a thrilling field right now.
It really is.
If anyone is going to figure out how to print the steering wheel for Feynman's microscopic surgeon, it's the folks listening right now.
Go.
Keep pushing the boundaries of what your lasers can do. Keep finding new ways to bend the light, and we'll see you on the next deep dive.